Let's recap. You are symmetric about the x-axis if you replace y with negative y and get the same equation. Looking at this example, I have a point, let's call this x comma y. It gets reflected across the x-axis to the point x comma negative y. So it would have symmetry about the x-axis. If you're going to be symmetric about the y-axis, you have to replace x with negative x and get the same equation. Let's consider the point x comma y. It gets reflected to the other side to the point negative x comma y, and that's why it's symmetric about the y-axis. If you're going to be symmetric about the origin, you have to replace x with negative x and y with negative y, and the equation is unchanged. So let's consider the point x comma y. It would be reflected across the origin, this point, the origin, to the point negative x comma y. Even and odd functions. A function f is even if f of negative x gives us the same function back for all x in the domain of f. Its graph is symmetric with the y-axis. A function f is odd if f of negative x equals negative f of x for all x in the domain of f. Its graph is symmetric with the origin. Example 5. Let's decide whether each function defined is even, odd, or neither. Let's consider f of x equals 8x to the fourth minus 3x squared plus 1. We're going to start by replacing x with negative x. If we do that and we get f of x back, that implies it's an even function. If we get negative f of x back, we're going to call it an odd function. And if it's none of these cases, then it will be the neither case. So let's plug in x with negative x. F of negative x equals 8 times negative x to the fourth minus 3 times negative x squared plus 1. Negative x to the fourth, since this is even, is going to be a positive x to the fourth. This is squared. It's going to make this negative x positive, but there's still a negative 3 in the front, so it's negative 3x squared plus 1. This is the original function, f of x. So now we know that this is an even function. So f of x is even. Decide whether each function defined is even, odd, or neither. We'll start again by replacing x with negative x. If I get the original function back, f of x, I know this is even. If I get negative f of x back, I know this is odd. And if there's a situation where it's not either one of these, it must be the neither case. We'll start by replacing x with negative x. F of negative x equals 6 times negative x cubed minus 9 times negative x. Since the exponent is odd, this is going to yield a negative value, negative 6x cubed, and negative 9 times negative x is positive 9x. It looks a lot like f of x, but there's negatives here, and this is positive, so let's try to factor out a negative to the front. I have 6x cubed minus 9x, and this looks exactly like f of x, and in fact it is equivalent to negative f of x. So this implies that it is an odd function. It is symmetric about the origin. It is an odd function. Decide whether each function defined is even, odd, or neither. We'll start by replacing x with negative x. And we'll see if we get f of x back, which means it's even. If I get negative f of x back, I know it's odd. And if it's not one of these, it must be the neither case. F of negative x equals 3 times negative x squared plus 5 times negative x. Since this is even, it's going to give us a positive value, 3x squared minus 5x. So it's not equivalent to f of x or negative f of x. Therefore, it is neither. It is not odd or even, it's neither. Example 6, we're going to graph the function g of x equals to the absolute value of x minus 4. Let's break it down into a simpler function. We'll start with the absolute value of x first. We'll create two columns. One column is going to be f of x equals the absolute value of x. And the second column is the graph that we want to do. The absolute value of negative 4 is 4. The absolute value of negative 1 is 1. And the absolute value of 0 is 1. Absolute value of 1 is 1. And finally, the absolute value of 4 is just 4. Now, if you look at the second column, the only difference is this negative 4. So we're going to subtract 4 from each of these in this column. 4 minus 4 gives us 0. 1 minus 4 gives us negative 3. 0 minus 4 gives us negative 4. 1 minus 4 gives us negative 3. And finally, 4 minus 4 gives us 0. Now we'll have the numbers to graph. In red is the original parent graph. Negative 4, 4, negative 1, 1, 0, 0, 1, 1, and 4, 4. Notice what happens to the graph when we have a negative 4 on the outside. It shifts all of these points down 4. It shifts all of the corresponding points down 4. Given a function g defined by g of x equals f of x plus c, where c is a real number, then for every point x, y on the graph of f, there will be a corresponding point x, y plus c on the graph of g. The graph of g will be the same as the graph of f, but translated c units up if c is positive. If c is positive, we're going to shift the graph up c units. And if c is negative, there is a vertical translation down of c units down. Let's graph g of x equals the absolute value of x minus 4. We'll break it down again with the original graph of the parent, the absolute value of x, and then we'll graph the absolute value of x minus 4. Let's create two columns. One column is the parent graph. The absolute value of negative 2 is 2. The absolute value of 0 is 0. The absolute value of 2 is 2. The absolute value of 4 is 4. And finally, the absolute value of 6 is 6. Now, I could pick any point I want for x. We're just going to pick a couple points here so we can see the shape. Now, for the absolute value of x minus 4, I'm going to plug in the 2 into x and then subtract 4 and evaluate the absolute value. For g of x, we are going to plug in our values of x, then subtract 4 from it, then take the absolute value. So let's try it out. Negative 2 minus 4 is negative 6. Take the absolute value, it's positive 6. 0 minus 4 is negative 4. Take the absolute value, get positive 4. 2 minus 4 is negative 2. Take the absolute value, it's positive 2. 4 minus 4 is 0. Oh, that's just 0 when I take the absolute value. 6 minus 4 is 2. The absolute value of 2 gives us 2. The original graph is in red, and you could do that by plotting the points like we did earlier. Now notice what happens when there's a -4 inside the absolute value. It actually shifts the graph. If you look at the points on the graph, the points are shifted 4 units to the right for the vertex, and similarly for each of the points on the graph, all of the points are shifted 4 units right. This is a -4 on the inside, but it actually shifts it to the right 4 units. It's kind of opposite of what you would expect. So let's look at the example. Here we have the original function f of x. If there is a +2 on the inside of the function, it actually shifts it to the left 2 units. The graph gets shifted to the left 2 units because of that +2 inside the function. If we have an x -3, it actually shifts our graph to the right 3. The graph gets shifted to the right 3. It's kind of opposite of what we think. Let's graph the function f of x equals negative the absolute value of x plus 3 plus 1. Now there's a lot going on in the problem. We have a negative in the front, so I know there's a reflection. There is a +3 on the inside, so we are going to have a shift left of 3. Remember, on the inside it's a +3, so we're going to go opposite, go left 3. And the 1 is going to tell us we're going to shift the graph up 1. For these problems, I like to make a table. We'll break it down into sections. Let's pick some values for x, -2, -1, 0, 1, and 2. And we'll try to work our way from inside to out. That's the easiest way to graph this function. So we'll start by doing x plus 3. That's the inside of the function. Let's graph the function f of x equals negative the absolute value of x plus 3 plus 1. There's a lot going on in this function. We have a negative in the front, so I know there's a reflection that's going to happen. There's a +3 on the inside, so that's going to cause our graph to shift left 3. Remember, it's going to go opposite of what we think because of the plus sign. It's going to go left 3. And this one is going to cause a vertical shift up 1. To do this problem, it's easy to break the problem down into different sections, and then we'll be able to plot some points. So let's create a chart of different sections of the graph. We'll start by listing some values of x, -2, -1, 0, 1, and 2. And here I'm going to work my way from inside to out, just like the orders of operation. I'll start with x plus 3. Then we'll do absolute value of x plus 3, negative absolute value of x plus 3, and finally at the end we'll have the complete function on the right. Now you could do it many different ways. You could have just 2 columns or 3 columns or more depending on the problem. So let's plug in -2. -2 plus 3 is +1. -1 plus 3 is 2. 0 plus 3 is 3. 1 plus 3 is 4. And 2 plus 3 is 5. Take the absolute value of these numbers, gives us the exact same numbers back. Now, in the third column here, we are going to have a negative in front of the absolute value, so each of our numbers suddenly becomes negative. And at the very end, we have the final function that we want, the absolute value of x plus 3 with a negative in the front plus 1. So all I need to do from this column to this column is add a 1 to it. -1 plus 1 is 0. -2 plus 1 is -1. -3 plus 1 is -2. -4 plus 1 is -3. And finally, Negative 5 plus 1 is 4. So now we can plot the points. Let's look at the graph of the function f of x. And notice that there is a reflection, and it did shift to the left 3, and there was a vertical translation of 1, just like we predicted earlier. Let's graph h of x equals the absolute value of 2x minus 4. To do this problem, I can see that this looks like they both have a factor of 2. So let's factor out the 2 to the front. I have 2 times the quantity x minus 2. And since this is a positive 2, I can actually take that out to the front, like so. And the absolute value of 2 is just 2. So this is the function we're actually trying to graph. We're trying to graph 2 times the absolute value of x minus 2. The best way we can do this is again to break the problem up into something simpler. Let's make a column of x values, negative 2, negative 1, 0, 1, and 2. Remember, you can pick any values, but I like to pick these values here. And we'll start our way in to out. So inside we have x minus 2. And then we're going to break it into the next one, which is the absolute value of that. And finally, I'll have the function that we're looking for. Negative 2 minus 2 gives me negative 4. Negative 1 minus 2 gives us negative 3. 0 minus 2 gives us negative 2. 1 minus 2, negative 1. And the last one, 2 minus 2, is just 0. All of these are going to be in the absolute value, so they'll all be positive. This is 4, 3, 2, 1, 0. And now in the last column, we're just going to simply multiply all of these by 2. So that's 2 times 4, that's 8. 2 times 3 is 6. 2 times 2 is 4. 2 times 1 is 2. And 2 times 0 is 0. So now we'll be able to plot the points on a graph, and we'll see what this looks like. Let's look at our graph now. And the red one is the original parent graph. The blue one is the graph shifted to the right 2. And we have a vertical stretch. Let's try the graph of g of x equals negative 1/2 x squared plus 4. Notice that the 4 is going to cause our graph to shift up 4. And this negative is going to cause a reflection. And that 1/2 is going to shrink our graph. To do this problem, I like to make, again, columns to separate the graph into simpler terms. Let's try negative 2, negative 1, 0, 1, and 2. And I like to work my way from inside to out again. So we're going to have to deal with the x squared first. So we'll do x squared. And then we'll have to deal with the negative 1/2 in the front. So we'll have negative 1/2 x squared next. And finally, we'll have the complete function negative 1/2 x squared plus 4. Negative 2 squared is 4. Negative 1 squared is 1. 0 squared is 0. 1 squared is 1. And 2 squared is 4. Now, in the second part, we need to multiply this by negative 1/2. 4 times negative 1/2 is negative 2. 1 times negative 1/2 is negative 1/2. 0 times negative 1/2 is 0. 1/2. 1 times negative 1/2 is negative 1/2. And 4 times negative 1/2 is negative 2. In the last part, we need to add the 4 to each of these. So negative 2 plus 4 is 2. Negative 1/2 plus 4. We're just going to convert that to a decimal. It's easier that way. So we'll say 3.5. 0 plus 4 is 4. Negative 1/2 plus 4 is 3.5. And negative 2 plus 4 gives us 2. Let's graph the curve. And here we go. We have the function does get shrunken up a little bit because of that negative 1/2 in the front. It is shifted up 4, and there is a reflection.